All right, so today we're going to talk about what light actually tells us about the structure of the atom. And everything we've talked about to this point just has to do with the nuclear model of the atom, where the electron cloud is all around the outside of the atom. But we haven't really talked specifically about the structure of that electron cloud. So as it turns out, we actually have to look a little bit closer at the nature of light and how it interacts with atoms in order to really understand those electrons and how they fit in the electron cloud. Okay, so the first thing we have to understand about light is that it travels as waves. So you can kind of think of the anatomy of a wave as kind of like this, like waves on a lake or waves on the ocean. They each have a wavelength. Wavelength is going to be the distance between identical points on two consecutive waves. And it's measured in meters. You could measure it in nanometers or centimeters if it's a small wavelength. We also have frequency, which is, they both have Greek symbols, by the way. This is the Greek symbol lambda. This is the Greek symbol nu, looks like a V. You can pretty much just write it as a V. But this is the number of waves to pass a point per second. So the closer the waves are together with light, the more of them will pass a point per second, because it turns out that all light, whether it's visible or invisible, like UV or infrared or microwaves, it all travels at the same speed. Okay, so the closer the waves are together, the more of them you'll have passing a point per second. And so that basically gives us an inverse relationship. So you can see here in this picture, we've got myself here. We've got shorter wavelength leads to higher frequency, longer wavelength leads to lower frequency, right? So that's just what an inverse relationship is. And so one way to write that mathematically is to say that frequency is proportional to 1 over frequency. Wavelength is proportional to 1 over frequency. Or if you want to use an equal sign, you would say wavelength equals c, which is a constant, times 1 over frequency. And it turns out that c value is actually the speed of light. So we rearrange the equation to get it out of the fraction form, and we see that the speed of light is equal to wavelength times frequency. So if c is a constant, the speed of light never changes. And so then if the wavelength is longer or bigger, the frequency by definition would have to be smaller. And there you see the value for the speed of light. And again, this is in a vacuum, so it does change a little bit as it travels through the atmosphere or through water or whatever, but this is the value that we use for the speed of light. Okay, so if we know this, then we should be able to solve a problem like, what is the frequency of radiation that has a wavelength of 455 nanometers? Now, we are going to have to convert that nanometers to meters, and we can do that in just a second. But first, here's our equation. We're going to try to solve for frequency. So hopefully you can see how we would get frequency by itself there, right? If it's being multiplied by wavelength, we would simply divide both sides by wavelength, and that would leave us with our useful equation. Frequency equals speed of light over wavelength. Go ahead and pause and give this a shot on your calculator. Remember that the speed of light is always 3 times 10 to the 8th meters per second. And also remember that nano is 1/1 billionth. So a nanometer is 1/1 billionth, or 10 to the 9th nanometers are in 1 meter. So you are going to have to convert that 455 before you can accurately do this problem. Okay, so there we are. That's what I got, my speed of light on top. You can see there. You can also see that meters cancel. And when they cancel, it leaves us with a placeholder in the numerator there, a 1. So our unit ends up being 1 over seconds, which are also sometimes referred to as hertz, H-E-R-T-Z, just named after a guy. But basically, it just means waves per second. But for math purposes, we usually use the 1 over seconds. So 6.59 times 10 to the 14th. So frequencies will generally be very large numbers like this. Okay, next question. What is the wavelength in meters of radiation with a frequency of 3.08 times 10 to the 11th hertz? So all you have to do here is rearrange our equation differently this time, right, which would give us wavelength equals c over frequency. And from here, we're just plugging in the values. Just remember that hertz means the same thing as 1 over seconds. So go ahead and pause and give that a try. Okay, go ahead and let's see what we got. Hopefully you're in the ballpark or exactly at 9.74 times 10 to the negative 4 meters. Okay, so there's our wavelength. All right, so the next question is, just for context, are either of these visible to humans? And to get, the reason that I just bring up this question is just to get you thinking about the entire electromagnetic spectrum. And so we have radio waves, which are really long and low frequency, then microwaves, infrared, and then this tiny little sliver from 780 nanometers to 380 nanometers is what we are able to perceive as human beings. So only that little bit. But the only difference and the only reason for that, it's not the nature of the actual radiation, it's just we have not evolved to see those other frequencies and wavelengths of light. So ultraviolet, of course, we can't see, X-rays we can't see, and gamma rays, which would be really, really short wavelengths, we can't see. All right, so this first one is 455 nanometers. That would be kind of actually on the upper end of a frequency, lower end of a wavelength for visible light. So it's probably like green or greenish blue light. So yes, we could see this one. The second one, though, is actually a pretty large wavelength. So it's probably in this neighborhood right here with infrared radiation. So just to kind of put it in perspective with maybe some of this other radiation that you've heard of before, to give you an idea, visible light is just light that we as humans can happen to be able to see, but its behavior and its speed and all that stuff is just like microwaves, radio waves, X-rays, you name it. Okay. We also need to talk about how this relates to energy. It turns out that the higher the frequency of light is, the higher its energy. Okay, so that's a direct relationship. And it gives us the equation E equals H times frequency. So energy equals H, which actually is a constant. It's called Planck's constant. All right. And so that number, 6.626 times 10 to the negative 34 joules times seconds, is what relates energy to frequency. But because we're multiplying these two, that means that, because energy is on the other side of the equal sign, that means as frequency goes up, energy has to also go up. So they're directly related. Okay, so let's try this one. What is the energy of radiation with a frequency of 3.45 times 10 to the 16th hertz? This one you don't have to rearrange, right? Just remember that hertz means the same thing as 1 over seconds. So go ahead and give that a try. Okay, let's see what we got here. Again, it was just plugging stuff in. And I got 2.29 times 10 to the negative 17 joules. Okay, just pretty much straightforward. Just have to cancel your seconds when you're done so you get joules as your unit for energy. Okay, this one's a little bit more involved because it's asking us for wavelength if we start with energy. But as we can see, wavelength is not found in the energy equation, and vice versa. We do know, though, that frequency and wavelength are inversely related. So what we can do is a little bit of substitution. So if I want to get wavelength into the energy equation, and I know that frequency is equal to the speed of light divided by wavelength, I can simply substitute frequency for what it is equal to, which is speed of light over wavelength. And then I come up with an equation that has both energy and wavelength. Okay? And if you prefer it rewritten this way so that both h and c are kind of in the fraction together, doesn't really make any difference. All right. Now the last step is going to be, I'm not solving for E, I'm solving for wavelength, lambda. So I will have to get the wavelength and the energy, basically have to have them trade places. Because to get wavelength by itself, I would have to first multiply both sides by wavelength, then divide both sides by E. So that would land me here. Okay, so go ahead and pause and plug in your variables. Well, actually, it's going to be two constants and one variable, and solve for your wavelength. Okay. So you should have hopefully gotten about 2.80 times 10 to the minus 7 meters. It's hard to do a mental check with these problems, by the way, because wavelength and energy and frequency, they can all vary by a lot. So wavelength can be 10 to the minus, 10 meters. It can be 1,000 meters. They can really vary. Okay, so the last step here is, what in the world does all this have to do with the structure of an atom? I told you that's where we were going with this. So connecting light energy to atomic structure, what do the two have to do with each other? First thing you have to understand is that atoms give off light after they're heated. So if I heat up a piece of metal in a flame, that metal is going to give off light. And the way that was explained by a scientist named Niels Bohr is he thought that the atoms were absorbing energy in the form of heat, and that energy was exciting electrons, moving them further away from that positive nucleus. Because they're negative, they don't want to be far away from the nucleus, but just like gravity pulls things towards the ground or towards the earth, with added energy, we can pick it back up. Well, if we add energy to electrons, we can pick them up to what we call excited states. And then when they fall back down, they're going to give off the same amount of energy that they absorbed. But this word right here, discrete, is really important. Because unlike dropping an object like a ball, I can drop this little molecule model from, just about any height I want to. And it would therefore hit the ground with a different amount of force every time. And there's an infinite number of different heights I could drop it from, and therefore an infinite number of different energies it could give off as it falls. But electrons don't work that way. They only rise and fall by discrete amounts. Kind of like climbing a ladder, you can only be on the first rung, the second rung, the third rung, the fourth rung. So you can only be at those different heights on the ladder, right? So electrons kind of work the same way, and Bohr figured this out. And so he came up with a very important part of the atomic model, which is to say that we have energy levels. So, and this was because, again, the energy required to excite an electron up to, let's say, from the first to the second, or from the first to the third, or the first to the fourth, or whatever, that energy was in discrete amounts. So the number of joules required to do that, and therefore the number of joules given off as they fall back down after they've absorbed that energy and they're ready to give it back off, is discrete. And it corresponds to different wavelengths of light. So as the electrons fall back down to their ground state, they give off these discrete amounts of energy in the form of visible light. So we'll see different elements giving off different colors based on where the electrons are jumping and falling. And we'll actually get to see that in the lab later on. All right, guys, that is it. Please rewatch if you have any questions or confusion, and bring your questions to class.